Hello, can everyone hear me? Okay, well, seeing something in the chat, I'm hoping there are people there. Hello, hello. Okay, so I'm Dave Ojha. You may know me online as Valor Dragon, especially on GitHub. So today I'm going to be talking about our vision at Sikka for ABCI++. Now, essentially, improving the interface for what an app can get out of Tenant. So the plan for the talk is to go with, first, what is ABCI? You may or may not have heard this floating around a lot. Then what sort of limitations does it impose right now? Then we'll walk in detail through the current form of ABCI. Then we'll talk about ABCI++. And finally, just a brief overview at the end about modularity and pluggability in Tendermint overall, or our view on this. So without further ado, ABCI. So ABCI essentially is an abstraction layer between how you write a blockchain and consensus. So it literally stands for application blockchain interface. So the feature of this is like when you go to write a blockchain, you don't have to think about mempool logic, how Tendermint works, or how is a transaction going to be gossiped in the network. You just have to code the answer to the question, how should I be executing my transaction? So this is a huge feature to have. So this is why in the SDK you can just have the nice modularity for app, and you define transaction types, and then you just define what you do with it. But there's actually a problem here, which it's not you only have to code this, but also you can only code this, and so that problem is going to be the heart of the talk today. So okay, maybe it seems like a nice abstraction, but there's a lot of things we want to add in to be able to do. Here's just a smattering of the GitHub issues that have appeared over time for this. And if we take a step back, the problem is the state machine doesn't know it's a distributed system. So this seems like a really nice feature, actually, because it is nice that you can make a blockchain and not know what's going on underneath it. You can sort of execute it like a normal state machine, like you think of in CS classes. But and so when you go to write the blockchain, you only have to code, this is how to execute the transaction or a block. But it's this exact interface that's going to cause, that limits us. So to get a sense of this, why is it, or where is it limiting us? So today there's a bunch of things we want to be able to add. So threshold encryption. So see Sunny's talk that's coming up next for how threshold encryption gives you ME resistance and or censorship resistance. You want data availability proofs. See the Lazy Ledger talk tomorrow. We also want the ability to soft fork. To give some context on this, it's actually really important. In the Cosmos Hub, there's governance proposal number 8, this emergency hard fork. Essentially at the time, there was this bug in staking that was really subtle, which let you craft a certain type of transaction that would yield an invalid state transition. And this is a bug that could be detected ahead of time, before you execute it. So this is something that could have been soft forked. But the problem we had was there's actually no way to allow soft forks over ABCI nicely. Your blockchain, the application part that you write, the part that knows what is a staking transaction, couldn't look at a transaction until it was already in the block and already ready to be executed. And since this is blockchain, you can't change the code you're executing without a hard fork. So you could soft fork this by saying that no one's going to vote this block is valid until if it has this type of transaction. But since we didn't have the soft fork, we followed back on this method of hard forking, and it was actually set up really well given the constraints. This is an emergency, but the communication between validators was not live enough. Not everyone got the memo that it's a hard fork's about to happen. So a couple of validators got liveness slashed. So this motivates the need that we do really need to be able to soft fork in applications like today. Some other features we want to enable is random beacons. I remember, I believe D Gaming actually implemented random beacons because they needed secure randomness in gaming things. And you can also want secure randomness inside of consensus, for your validator election. So these are important things that we have projects in the ecosystem needing. Then, if we step back for a second, there's actually a lot more other things you can do with the blockchain that we could enable with some ABCI changes. So one is like scaling things. Your application at the moment is tied to like a single execution model, where essentially once a block is finalized, I can then operate transaction by transaction. So, but a lot of scaling things actually operate in a different way, where you have the proposer or a validator do extra work, and then all full nodes can do less work. So examples of this are like succinct blockchains. You may be familiar with Mina, which uses recursive snarks. Mina Mina was previously known as Coda a while ago. And you can use snarks for just a single block at a time. This is what all zk rollups are on Ethereum. You can allocate all your transactions in a block. So currently, when the bulk of your computation time on the hub and most chains, well, I guess some of it's encoding, but in principle, it's all would be signature verification. And so you could do like some cryptography tricks to say like, okay, if I need to verify n signatures, I can verify this in much faster, or I can compress n signatures together in certain ways. Then you may have heard of Mimblewimble. This is what Grin and Beam, which are different blockchain projects, implement. Then one of the key ways that you scale blockchains, like the memory requirements of blockchains, is by being what's called stateless. But being stateless also has actually really bad UX problems. So you can you could want to have a good UX plus statelessness, which is what this means by stateless blockchains with validator provided auth paths. So that's what Mir is doing, and potentially ETH2. I don't think ETH2 is finalized on how the UX versus full node validator efficiency trade-off is yet. And you can want pipeline block execution models. I can talk about this at the end if people are interested. Just ask a question at the end. So then another thing we could want, which is to further rely on our validators. At the moment, your validators are responsible for finalizing blocks, but you can want them to do more. So capabilities we want. Validator backed price oracles. So at the moment in ETH, you have a chain link which has a couple of centralized nodes tell you the spot price of an asset. But you could want your validators to do that themselves, because you already have a 2/3 honesty assumption on your validator set because of security consensus. So if you did this, you could get a threshold that you already trusted for no new security assumption, the spot prices. You could then also get the guarantee that this will be included in every block. That's a nice new feature to have. Another is validator guaranteed IBC connection attempts. You can make sure your validators do IBC connections every block, and this actually lets you reason about the liveness of another blockchain, which could be very useful for shared security. You can want random beacons. I talked about that on the prior slide a bit. And random beacons fundamentally, well, 2 of the 3 most popular ways for doing it require your validators to do more. E.g. VRFs or BLS threshold beacons. You could want threshold encryption, which also requires your validators to decrypt transactions. And here's an interesting one. So at the moment in Tendermint, a proposer can just sort of propose transactions that are basically random. You could propose a block filled with kind of random bytes, and then all the nodes receive it, finalize it, and then only later do they realize that this block kind of was filled with useless stuff. So you could restrict your blockchain to only allow proposers to propose useful things. This is a thing one could want. Then some more nuanced things is you could have data availability proofs with just your validator set, or you could have you could want to shard computation across your validators. I don't know, if you had some large computation you want to do every block, you could then shard it between the validators and be guaranteed it's going to be included. And there's more about these lists. So let's move on to what is ABCI right now, and why is it not letting us do this stuff? These exciting things. So I mentioned earlier, ABCI is this intermediate layer between that defines how is our state machine, our application, going to talk to consensus. So let's break this up into what are the steps of consensus. So in Tenor in particular, you have a proposal phase, pre-vote, pre-commit, and then its finalization phase. So the proposer is the one who proposes a block, and only the proposer has to propose a block. Then it's a kind of a detailed tenorement. You have 2 rounds of voting, and then if you get enough pre-commits, enough final votes at the end, let's say this was the right block, the block becomes finalized. If not, then you sort of loop around and someone else proposes the block, and so forth. And then ABCI only talks to state machine at one point. Once the block is finalized, the tenorement will then tell the application, like, okay, I'm now giving a new block, here's your transactions, okay, and now look, I'm done with the block. And this is the only point of communication. If you've developed an SDK, you may be familiar with checktx. That's actually not happening in consensus at all. That's something that only happens in the mempool. So the proposer is just going to do it locally for it to check, for its own purposes, that it's proposing something good. But other nodes in the network can't have no guarantees about it. That's not happening in your consensus protocol. So if we take a step back, and want to abstract around consensus a bit better, we can just combine pre-vote and pre-commit to just a voting phase, because it's kind of a detailed tenorement that there's 2 rounds of voting. We can have 3 rounds of voting, or that's what hot stuff is. Or we can have other consensus protocols that have a different setup. Basically most BFT protocols require some number of people to propose a block, then there's some process for voting on that block, and then you finally finalize it later. This is basically how all BFT protocols work, with the have guaranteed finality. So now let's talk about what are we going to do to change this to add more things. And we're going to propose this new sort of trifecta or trilogy of phases to ABCI. So prepare proposal, process proposal, and vote extensions. First, preparing the proposal. Essentially, we're going to have the proposer be allowed to talk to the application before it finally proposes its block. And so this is what's going to let us do a bunch of batch optimizations. So the way this works is the proposer gathers its proposal for the next block. A proposal is just a header for a block and the transactions for the block. It's going to go to the application and say, okay, prepare my proposal for me, prepare it for broadcast. And then you have a proposal for block n+1. That's going to be a process header and a process transaction. Okay, so this is the bug. Just say processed here. And this processing, application processing step is what gives you batch optimizations. So you could have the application take these raw transactions, parse signatures, and do some aggregation technique on it, and to give you the process transactions. This also lets you separate what is the data you need for the P2P layer, what's the data you need for the state machine. A common example, if you've been in the weeds of SDK, is what happens with transaction sequence numbers. Currently, in the mempool layer, in the application, we don't use we don't include it because you don't need it when you're processing a transaction. You already know it. But in the mempool, it's actually really useful for a bunch of reasons to still provide it. So you could use the same process to separate the data at these layers. And okay, there's another cool thing we can do here, where a lot of people need their own mempool, not they want to do custom logic outside the tenorement mempool. And essentially, we don't really understand how to best what the right interfaces are for a mempool. How do you abstract over what's the need for a mempool to talk to other nodes? But what we can do is we can allow your application to sort of sort or choose the order of transactions nicely. So you can use prepare proposal to sort of hijack the process and do this. So here's the steps for doing it. Whenever the mempool receives a transaction, it asks the application to verify it. So you can just basically log all those transactions inside the SDK, in your application. And then you can control you can tell Tenormint, gossip this or don't gossip this. And so this is what checktx does. You can reuse this for that purpose. And then you can make consensuses, whenever consensus says, prepare my proposal for me, you can ignore what the Tenormint mempool says and instead use your own application mempool. So essentially, you've allowed the application to sort of handle ordering via, it's do all sorts of different fancy things, packaging transactions together, etc. But it's using the existing Tenormint mempool logic for the P2P layer until we best learn how does one abstract mempools, mempool P2P dependencies. So this is exciting features. A lot of chains want different mempool orderings than what Tendermint provides. So on to the next phase then, process proposal. So essentially what's happening is a block proposer's proposed a block. Now all the other validators get a block in the network. And so they want to do some sort of checks on their own to say, is this valid or not? This sounds all like us enabling soft forks, which is exactly what this is doing. So we break this up into 2 steps. First, first you always get a block header, and then you want to verify the block header. And only if you get a valid block header do you actually want to get the rest of the block data. This is the way most blockchain P2P stuff works. So you have a method for verifying a header and a method for verifying / processing a block. So let's look at the exact APIs here. So when you receive as a validator, when you receive the next block's header, you just ask the application, is this block header valid? I guess for context, Tendermint's still going to verify is the block header valid, but your application can do additional checks on it. So it'll do that. Then once you receive the block data, you'll run process block via ABCI, and it basically gives your application the block data. And then the application can say, okay, was this valid or invalid? Is there something wrong with this block beyond the actual transactions in the block? And your application can do some other side effects. If you wanted to exit a block immediately, you could do so and sort of queue the changes right now. And then it's a bit subtle, but essentially, because the block's not finalized, you need a way to revert the side effects that I just mentioned above. So your consensus engine will call revert proposal if it didn't end up getting finalized later. So what are the effects of this? Essentially, alongside. Well, essentially, the method sends the proposal to the application, and so the application can process things. The most exciting features to add is soft forks. You can now soft fork because that's exactly just saying this block was invalid. There's some transaction in it, and it's a bit of a detail which I can go into if people have questions on it. But this is what allows different block execution models. And furthermore, you can have validator-dependent computation on blocks as soon as you get them. This is really good for threshold decryption or other optimizations one could want. So onwards to the final phase, vote extensions. So a vote extension is essentially when you vote on a block, currently you just kind of vote on the hash of the block. But now we're saying, I actually want to vote on hash of the block plus some other data that's my state machine is going to tell me. So there's really 2 methods here. One is I have to extend what is a validator actually voting on, and then we need to let the state machine also verify this additional data that the validator added. So go into a bit more detail of this. So we have an unsigned Tendermint vote. This is what the data you would be pre-committing on, and then the validator is. Then it's going to go to ABCI and say, extend this, add some more data to it. So here's the same unsigned Tendermint vote. Then there's 2 sections of application vote data. So you can think of application vote data as sort of the spot price of an asset, if in the case of using validator-backed price oracles. So then what you're going to do is you're going to use existing Tendermint API for please sign this vote for me, which will then sign the Tendermint vote data as before. And it's also going to sign over this application vote data. And it's going to have a vote signature. So you may be wondering, what is this authenticating app vote data? Essentially, that's you can have the application add something to a vote which doesn't need an initial signature. This is kind of a complex detail that comes up for certain things like threshold decryption, where you want batch optimizations later. So when you receive someone else's vote over the network, then you essentially, Tendermint's going to verify the signature. So it'll check the Tendermint vote data is valid, just like now, and it'll check the signature is valid. Then it'll say, app, please check that the data you care about. Was it valid? Was this a valid spot price? Syntactically. So there you call ABCI again, and it'll do so. And then it'll tell you, was the app vote data valid or invalid? Invalid, reject the vote. If it's valid, then great. Proceed as tenor normally proceeds, or your consensus normally proceeds. So this is what enables the validator-backed price oracles, validator-guaranteed IBC attempts, random beacons, and threshold encryption. For some of these, you need the other methods for efficiency reasons as well, to get reasonable efficiency. But it's the vote extension that's fundamentally letting your validators do more work every block. So if we carry this through, those are 3 new phases, but something subtle happened. Once we did process proposal, we gave the application the block data. So we don't need to have delivered TXs anymore. So this means that we get this nice new model for once a block is finalized, Tendermint just has to tell the state machine that block is finalized. In the current SDK, if you want the current SDK's functionality, then you can, then this would just be the equivalent of begin block, deliver TXs, end block. No change there. But if you wanted other functionalities like immediate execution, where you executed the block over here, then this will just be saying, okay, commit those changes to disk. So this lets you get abstract over how your block execution model. So I guess now I want to take a step back and look at modularity and pluggability in Tendermint overall, or this stack overall. This is something Tess talked about in her talk earlier today. So there's application pluggability, which let's just say plus. Whoops. Is application pluggability, which is being handled by this new ABCI method. And there's pluggability within Tendermint core. Tendermint is a consensus algorithm, consensus engine, and you can want pluggability inside of it, which is something different. And there's sort of 2 different classes, I'd say, or that I understand at the moment at least. Cryptography pluggability, aggregate signatures in consensus, or changing the hash function. Maybe I want to use Blake2 for some reason, or I want to use a snark-friendly hash function like Poseidon. There's also P2P pluggability. So one is improved block gossip algorithms, like Raptor encoded block gossip, what Solana and Harmony and some other chains uses for improvements there, or Bitcoin compact blocks, etc. And there's improved transaction gossip. This ties into the whole how should we best abstract over mempools needs to talk to other mempools. So the bulk of the main thing we're handling is application pluggability via ABCI++. And so a question that may strike out is why is aggregate signatures not handled via ABCI and the prepare proposal? And that's actually, I think, an abstraction violation, because that would mean that ABCI has to handle signing votes. And that's no good. Tendermint fundamentally is about validators and signing votes and verifying votes, etc. So this would not be a good we should not have application think about how do you sign. So in summary, we propose solving a lot of the application pluggability needs in Tendermint by adding 3 new ABCI phases: prepare proposal, process proposal, and vote extensions, leaving this diagram for what is ABCI, what does ABCI look like, and how does it talk to that. Great. Thanks for your time. Please ask any questions. I guess I'll switch to looking at Crowdcast now. Let me go back a slide. Okay, does adding mempool ordering to ABCI mean defining the order in which transactions are rebroadcast, or defining which transactions are validated locally? Okay, so adding mempool ordering to ABCI. Okay, so if you want an app-defined mempool, it would mean having your application basically choose what transactions to gossip and how do you bundle transactions to gossip, and also choosing what order to include them in the block. So currently the mempools just gives you a list of transactions and you include those directly in the block. But you could want to order them differently. That's one part of an application-defined mempool. A second thing is you could group them together differently. So if you're familiar with Mimblewimble, a thing you do there is you bundle transactions together. You aggregate their signatures and essentially their data to get sort of the privacy properties you want in on-chain and efficiency properties. Similar thing applies to Zcash or Stolon. You change how you bundle transactions together to get better guarantees for private transaction gossiping. Does that answer the question, Lakshman? Okay, I guess I was skipping to the next question I see. Bucky is saying, won't threshold decryption make soft forks impossible again? Yes, it does. But it's worth it, I think. Yeah, you'd have to hard fork where soft fork needs, because you can't see the transactions. So I guess that is a trade-off. You could have some subset of transactions non-encrypted if you wanted. That's how you design that's how you want to design your blockchain. In which case, you can still soft fork for the unencrypted transactions. Yeah, I don't see any other questions. I guess anyone else want to ask anything? If not, it's going to end early. Happy to talk about any of the scaling solutions or anything I brought up in the talk in more detail if someone wants. People this. Hey, Jeremiah. Jeremiah's asking, couldn't you create some sort of post-decryption soft forking check? I don't think it's a soft fork at that point, because if you do it after you decrypt a transaction, then it's already like in the state machine. So it would have to be a hard fork, then like not decrypt a transaction. Or sorry, to not execute a transaction you decrypted. I hope that answers the question, Jeremiah. Or maybe I'm missing something. Oh, okay. Dean's asking, can you talk about how this improves transaction pipelining? Okay, so maybe there's two fronts. One is in for transaction execution. Something we currently had in the ABCI model was I give you transactions one by one. So then on the app side, if you want to do parallel execution, or you wanted to do sort of batch execution, then I'd have to like queue it on the app side. Whereas now, since we have the block data given all at once, you can do some sort of execute in batch or parallel execution. That's actually not, I don't know, that's not a really big difference. When I was meaning pipelining before, I was actually talking about something more at a block level. So at the moment, let me scroll to the ABCI as it is right now slide. Can you still see my screen? Oh, rip. Okay, let me reshare that. Okay, let me reshare the current slide. Or sorry, the slide of ABCI right now. Okay, so essentially, and the way it is right now, you execute a block after it's finalized. So you're executing block n+1. But you could want to execute like the current block here. Okay, I didn't really plan the slide choice or what slide to look at this on very well. Okay, nice. So essentially, currently you execute a block after it's finalized. So when you receive the proposal for block n+1, you're executing block n. But you could want to say, okay, when I receive the proposal for block n, I execute it immediately before I vote, is it valid or not? You could also want to say that when I receive a block proposal for n+2, that's when I'm executing block n. Or that's when I have to finish executing block n by. So essentially, you can add a bigger pipeline. So maybe an example of why this makes sense is if you're doing like snarks, so recursive snark blockchain, similar to Coda style, well, creating a snark on a blockchain takes time. So maybe it takes, I don't know, 10 block times to make a snark proof that it's valid. So I could want to finalize a block first, but then require that by only once I get the full proof of it being valid by block n+10, do I execute it fully. So you can like change the time between when a block is finalized and what's the block you're executing. So you can currently consider like there's a block pipeline of 1 right now. So I execute block n when I receive block n+1. But you can want a block pipeline of 0, sort of immediate execution, ETH and Bitcoin style. You can want a pipeline of 2, 3, etc. Okay, I think that answers the question. Okay, I think this. Oh, there's another ask question. Oh, it's the same one. Okay.
Cool. So we're gonna transition to the next talk then. Oh, there's another question.
I don't. Sorry, maybe we can talk about that offline. I'm not too sure what that is.
Okay, awesome. Thanks so much for the great talk. We're gonna transition